Okay, so welcome to today's talking seminar. Our speaker today is Ravi Srinivasan, and he'll talk about complete reducibility of differential central simple algebra.
Uh, Thank you, Michael, and I thank the organizers for inviting me. It's good to be back and very happy to give this talk. In this talk, what I decided to do is, explain a bit of the theory, and then I will show the work that I have done with my PhD student Manujit. So this is actually a joint work with Manujit Michael. So central simple algebras, the central simple algebras we will look at are basically over fields of characteristic zero. So we will fix a field of characteristic zero. And then, so basically a central simple algebra is a finite dimensional algebra over the field, and the center is F, and it has no two-sided ideals. And the differential counterpart is basically it's a central simple algebra with a derivation on it. So this is called central simple. So any derivation on the central simple algebra will actually map the center to itself. So basically, then this nabla A that we are considering, that is going to restrict to a derivation on the field. So we can just simply talk about central simple algebra with a derivation, and that will already make the algebra a differential F module. So that is
sorry for the interruption. Just to clarify, so F is a differential field in that case.
F will become a differential field. So you start out with a central simple algebra with a derivation. So this derivation is just a derivation as a ring. Then what it's going to do is, if you look at the relation, so the center basically commutes with all the elements of A, right? So if I look at Fx equals Xf and then apply the derivation, then you will see that F dx and dxf, they will cancel out. And then what you get is df will commute with all the elements, and therefore df will belong to F. So, so it automatically, it will make the central simple algebra into a differential F module. So that is important for the rest of the talk. And so naturally, if I have a matrix algebra over a field, then there is this natural derivation, which is called the inner derivation. So these are, immediately seen to be a derivation, and they restrict to the zero derivation on F, because the center will, the center will be killed by this commutator, right? So, then the question is, what are all the other derivations? So if I look at the mapping from M and F to F, if I look at the mapping from M and F to itself, then so that is given by this coordinate wise one. So for this, we are now starting with the differential field, and then you can put the coordinate wise derivation, and that will give a derivation on the matrix algebra. The reason I look at this is because this is the simplest examples of central simple algebras over the field. So it's matrix algebra over F. So that is a central simple algebra, and you have this natural derivation. And then what one can also do is you can add the inner derivation to this coordinate wise one, and you get more derivations, right? So then the question is there any other derivation besides these on the matrix algebra? So so there are two questions. What are all the derivations on M and F? And then you can also ask, how about in general central simple algebras? So here what I am asking is essentially, you don't have to fix any derivation. You can simply ask can you classify all the derivations on central simple algebra? So that also one can do. So what we have seen is that if I have a derivation on the central simple algebra, then it restricts to the center, and therefore you get a differential field. So conversely, if you start with the derivation on the differential field, then how far you can go? I mean, the first two examples says there are plenty of derivations in the case of matrix algebra, but in general, if you have a central simple algebra, whether you can extend the derivation from the base field. So that is a question. And this question was first answered by Jacobson in 1937. So if you look at the trivial derivation, that is the zero derivation on the base field, then of course every inner derivation, as we saw, that will restrict to the zero derivation. Conversely, so what one would like to do is ask what are all the derivations that restricts to the zero derivation. Then Jacobson proves that they are precisely the inner derivation. Okay, so in particular, so if we go back to the original problem of extending derivation from the differential field to the central simple algebra, if I have two such derivations, if I have two extensions, they restrict to the same derivation on the base field, then their difference is going to be an inner derivation. So that is obvious because they both agree on the base field. So you take the difference, then it will be zero on the base field, and therefore by Jacobson's theorem, it will be an inner derivation. And this theorem in particular says that if I have just one extension, so if I just extend the derivation on the base field to the central simple algebra, then all the derivations are can be gotten by simply adding the inner derivations. So that is the point of this thing. So all we need to do is just extend the given derivation of the base field to a derivation of the central simple algebra. So this is essentially done by Hochschild in 1954. He proves this result that if you have a derivation on the base field, then you can extend it to a central simple algebra. In fact, he proves it in a much bigger context. So even if a subalgebra has some derivation, then you can extend that. So he proves it slightly the general context. And many of these results were reproved by Amitsur in 1983. And then for characteristic P setup and using this Hasche-Schmidt or this iterated derivations, so one can actually extend a derivation on a ring to any Asimov algebra. This was done by Roy and Sridharan, and also in a similar context by Knus and Barr in 1971. So now we know that central simple algebras, we actually know all the derivations of a central simple algebra in the sense that you extend one and then you get everything by adding the inner derivations. So derivations exist on any given central simple algebra. In particular, in our case, we will only work over differential fields. I thought I will give a proof of this. So let me quickly go through the proof. So the point is that the proof is slightly non-trivial. So what happens is one first extends the derivation of the ground field to a cross product algebra. So basically, a cross product algebra is given by some data. A Galois extension is given, a Galois group is given, and then a normalized 2-core cycle is given. So this normalized 2-core cycle is going to give you the multiplication on the span of, so basically you attach some symbols, E sigma, for sigma in G, and then this will be, so since the Galois extension is of degree n, so I will attach n symbols. And then the multiplication is given by this E sigma times E tau is F sigma tau, F sigma comma tau times E sigma tau. So this multiplication will become associative because F is a normalized 2-core cycle. And then E sigma times L is going to be sigma L E sigma. So using this, one can show this is in fact a central simple algebra. So now the point is basically that the logarithmic derivative map from L star to L is going to induce this map at the level of the second cohomology, the multiplicative one to the additive one. And the additive one is actually 0. In fact, any nth cohomology from the Galois group to the base field, this is going to be 0. And therefore, what happens is that this logarithmic derivative is in fact a co-boundary. So you can write like this. And then you use this U sigma to define a derivation. Nabla B of E sigma is U sigma E sigma. And then you show when you, so you have this relation E sigma E tau is F sigma tau E sigma tau. So you apply derivation and then, you will calculate, there will be an expression. And then you will see that this expression will happen only if this relation, the logarithmic derivative, is given by this. So this will just turn out to be the case when you do the calculation. So this is all required to show you can extend a derivation of the base field to any cross product algebra. So next, what one does is, given a cross product algebra, one knows that any central simple algebra is Brouwer equivalent to the cross product algebra, meaning M of A is isomorphic to Mn of B. You can find such M and N. And what then happens is, since we already have a derivation on B, you just put the coordinate-wise derivation on M and B. And then using this isomorphism, you transport it to something in MMA. And then finally, so you have a derivation on the matrix ring with entries from A. And he then, what he does is he finds a suitable inner derivation, and then he just changes the original one by adding this one. And he shows the scalar matrices. They are going to be stabilized by this new derivation. So you do get a derivation on the ring A. So the proof of this is that way. It is complicated. It is not that straightforward, but one can prove the existence this way. So next, what we will talk about is some application. Amitsur basically used derivations to essentially classify Brouwer group of central simple algebras over some field C. So you can think of C as a field of constants of some differential field K. Then this the Brouwer group of all central simple algebras split by F and K. That is, there are two fields which are linearly disjoint over C. So he then proves that the Brouwer group of central simple algebras which are split by both F and K is going to be this quotient group, where Fk plus is the additive group, and this L of Fk is this logarithmic derivative. The set of logarithmic derivative, which is going to be again an additive group. So he uses derivations to study Brouwer groups, and there's also a cohomological interpretation. The first Galois cohomology also, he shows it that group is in fact isomorphic to this one. The Brouwer group of all central simple algebras split by both F and K. So what we are interested in is it should be splitting. There is a L missing. So what we will be interested is to consider splitting, is to look at the splitting fields of differential central simple algebras. So in general, if you have central simple algebras, you have finite algebraic extensions splitting them. If the central simple algebras accept maximals of field, then that splits it. And also in general, there are Galois extensions splitting a central simple algebra. So similarly, if I am given a differential central simple algebra, the question is whether are there differential fields splitting them. So in the work by Magid and Juan, So what they have proved is that there are Picard-Vasio extensions splitting a differential central simple algebra. So I will also go through quickly the proof of their statement. So essentially what one does is first one splits the central simple algebra.
Quick question.
Yeah.
Before the proof, is it okay if I ask?
Yes, please.
Can you go back to the previous slide? Oh, yes. How does this translate into the language of differential equations?
So that I will actually show you. I think you have to see the proof.
Okay.
In the proof, you will see it.
Interesting.
Well,
all right, let's do that.
Yeah.
Thank you.
So, so the point is, first you split. You take a finite Galois extension and you split the central simple algebra, right? So then A tensor L becomes MNL, right? So then the A tensor L has this natural derivation. So you have the nabla A, and then you have L is the differential field. So that has a derivation. So then the tensor product of these two derivations will then can be transported to M and L. And what we saw is M and L will have this matrix P. See, the derivation on M and L will be the coordinate-wise derivation on L plus an inner derivation by P. Now, to answer Alexei's question, what you do is you take a Picard-Vasio extension for this matrix differential equation y prime equals Py, and then that Picard-Vasio extension will then split this differential equation. We'll split this differential equation and also split matlab, meaning this in this case the M and E dp, this derivation is going to be isomorphic to the coordinate wise derivation. Okay, so I will in a later slide I will actually show you that this is equivalent to the other definition of Picard-Vasio extension, which is essentially that you will have this if you tensor A with the Picard-Vasio extension, then it has enough constants. So the dimension of the constants will be the same as the dimension of the differential module. So and finally, what one does is L is algebraic. It's a Galois extension. So a Picard-Vasio extension of a Galois extension. And therefore, if you start with a finite Galois extension and then a Picard-Vasio extension, the entire thing can be embedded inside a Picard-Vasio extension. So you take that, and that one will end up splitting this. Okay. So this is their proof. Now, so the Picard-Vasio extensions can also be thought of as without appealing to the differential equation. One can talk about Picard-Vasio extensions of a differential module. So then that is basically the constants are going to be the same as the ground field, and then this M tensor K. So if M is the differential module, then M tensor K must be a trivial differential module in the sense that the number of constants, it should have enough constants. The dimension of the constant should be the same as the dimension of the module. And then if I take a basis of M, then and I write the constants in terms of the basis, then the coefficients of this basis should generate E. So that is this is an alternate definition of a Picard-Vasio extension. So using this, what we will show is that how one can split the central simple algebra by thinking of the central simple algebra as the differential module. So basically, I'm recalling this definition. So you say a differential field splits a central simple algebra if you have an isomorphism, differential isomorphism between these two K algebras. So what one can do is you think of A nabla A as a differential module. Then there is a Picard-Vasio extension which splits this differential module. Then the tensor product A tensor K will be trivial because by definition, K, we have chosen K to be Picard-Bessio. So A tensor K will become a trivial differential module. Then the subalgebra of constants, so that is this A tensor K, the constants of A tensor K, that then one shows is actually a central simple algebra over the constants of F. So once you prove this, then the fact that F nabla is the constants of F is algebraically closed is then used to show that the constants are basically isomorphic to the matrix algebra. So if you have a central simple algebra over an algebraically closed field, then all such central simple algebras are simply matrix algebras. And that is the reason that you have this isomorphism. And then finally, the last line is simply that A tensor K can be written in this case as a tensor product over, these two are essentially linearly disjoint. You can think of it like that. So A tensor K constants tensored with K, that is going to be isomorphic to A tensor K. And then since the first coordinate of this tensor product is, we just showed it is M and F, and then the equation then shows that A tensor K and M and K are isomorphic. Alexei, I'm sorry. So did I answer your question, or is this?
To an extent, but I'll ask it again.
Okay.
As you go.
Okay, no problem. So, so what this construction also tells us is that the Picard-Bessio extension thus gotten is essentially minimal, in the sense that if I have any other splitting field and such that the constants are the same as the constants of the base field, then this Picard-Bessio extension of the differential module A nabla A is going to split. It can be actually embedded inside inside this inside any differential field that splits A nabla A. So this is basically because the moment you take a differential splitting field, then what happens is you have so you already have this condition that the constants of K and constants of F are the same, and then you also know that the splits essentially means you will also know that this module is trivial. The only thing that you want to know is so what you can also do is that when you write the constants in terms of this basis, so we will basically be picking up certain elements from the field E that is splitting the algebra, and then you generate a smaller field. So that field by definition is going to be a Picard-Bessio extension because all these conditions are going to be satisfied. So any differential splitting field that you have for the central simple algebra A nabla A, so you can find the Picard-Bessio extension of A nabla A sitting inside that. So that way this is minimal. So the theorem that what we have proved is essentially that if I have a differential central simple algebra and the constants of F is algebraically closed, and then you take a Picard-Bessio extension for this module, and then the relative algebraic closure of F inside K is denoted by F naught, and then the differential Galois group is G. With this data, what one can say is the differential central simple algebra is in fact an internal direct sum of its minimal differential right ideals, if and only if the Galois group is a reductive algebraic group. And if the identity component of the differential Galois group is solvable, then the relative algebraic closure will split the central simple algebra. And you will also have a chain of differential ideals in where the dimension of the first one is n, and then the co-dimension is always 1, and then it builds up to the algebra A tensor F naught.
What is the differential Galois group of A delta A? Is that
So that
the
is
differential Galois group of K?
so the differential Galois group is essentially so this A delta A will have a so it has a different it's a differential module. It's a differential F module, and therefore you can take a
good.
basis.
No, that explains it. Thank you.
Yeah. So, so the proof, I will outline the proof. So basically, you have this functor from the category, the Tanakian category generated by A nabla A to the category of representations of the algebraic group. So in this, this functor, what the first step is basically to show that since we are working with algebras, so since A is a central simple algebra, the ideals, the differential ideals of A will be in one-to-one correspondence with G stable right ideals of this quantity, the S of n. So this is basically it is done exactly the same way as how you prove. It basically follows from the definition, except that you just have to use the fact that when you start with right ideal, what you end up getting is also a right ideal. So so this correspondence is first set up. And then what one observes is that, so you do have a representation of the group G into GL of SA that is given by this correspondence. And what you also see is, again, since we are working with algebra, the SA is basically A tensor K, the constants of A tensor K, and the group acts as actually automorphisms. So if you see the action is essentially on the second coordinate. And then you can readily see that the sigma is actually an automorphism. So therefore, what you get is that the representation is basically that these groups are sitting inside the automorphisms of SA. So that, which is nothing but the projective linear group, and therefore you do have a representation of G into the into PGLN of over the constants. So once you have this set up, the third diagram to keep in mind is, so you do now have a representation from G to PGLN, and you have this projection map from GLN to PGLN. So what you do is you just lift the image, and then there are now the group acting on MN S of A. So that is there as automorphisms. And you also have this group H, which is the pullback of the image. So that will actually act as automorphism of the vector space of constants, the n copies of that. That is the usual matrix multiplication. So what one sees is that the G stable right ideals of SA and the subspaces of this vector space are actually there's a bijective correspondence, and the bijective correspondence also respects the group action, the individual group action, where G is acting on the right ideals of SA and H is acting on the subspaces of CN. So using this and using this exact sequence that we have, that is basically coming from this the top diagram, which is that GM is into is embedded into H, and then H to G you have this surjective map. Then you show that G is reductive if and only if H is reductive. Similarly, if solvability also you have it. So in our case, since we are working over the fields of characteristic 0, so reductive groups, all the representations are completely reducible, and therefore, since your H is reductive, the vector space is essentially going to be a direct sum. And similarly, if G is connected solvable, then so is H, and then H will also have a chain like this. And then you use all those bijective correspondence So the first one is between G-stable right ideals and subspaces. You first use that, and then you will go to now SA, where you will have the flag of ideals, and then you use this bijective correspondence between differential right ideals and G-stable, and then finally you will end up in A. So, so essentially, by applying those bijective correspondences, you actually get the theorem. So that is the outline of the proof. Do I have some more? Do I have time till 9:30? Is it?
Yeah, you still have be good in time.
Okay, fine. So so that is so that's essentially the proof of this statement. So next, what we will see is that if I have a central simple algebra and if I have a maximal subfield, then you can always find a derivation stabilizing the maximal subfield. This is also in that Hochschild's paper from 1954. So this result has the following significance. So if the derivation stabilizes a maximal subfield, then what one can show is that the differential Galois groups, the identity component is actually a torus. So this this fact follows from the observation that so the way the proof goes, I haven't written it down. Maybe I can just essentially say what is the gist of the proof. So basically, you have you can take a Galois extension, the minimal Galois extension containing L, and then you can show that actually splits the central simple algebra. So in our case, you know, L is a separable extension, so so the L itself will split. Therefore, if I take the smallest Galois extension containing L, that will also split. And then what you do is you will be tensoring that Galois extension with A. And therefore, you will also be tensoring this L inside. And this L tensored with the Galois extension is going to split into a direct sum. So if we call that Galois extension as say K, then L tensor K will be n copies, where n is the dimension of L. So there is going to be this algebra map. There is going to be this L tensor K is going to be some n copies of K, and then what one observes is that A tensor K then will have this direct sum. So therefore, but then if you have any n-dimensional subspace which is just going to be this direct sum, that can be conjugated to a diagonal matrix. And then the point is you will then end up solving a matrix differential equation whose the matrix, the y prime equals py, where the p is going to be a diagonal matrix. So, but then we know how the Picard-Bessel extension is going to look like. They are all going to be exponentials of this diagonal entries, and for that reason, you actually end up getting a torus. So there is this question which I do not know a full answer. It's basically that if I have a differential central simple algebra, and if I restrict the derivation, I assume that when I restrict the derivation of A to the base field, the constants will be algebraically closed. Now I take a Picard-Bessel extension and I take this relative algebraic closure. So the question is, does the relative algebraic closure split A? So this is the case when the connected component of the Galois group is solvable. So that is something that we you know, I didn't completely explain that part, but that is built into that theorem. But otherwise, it doesn't seem to be. However, there are these cases where if the Picard-Bessel ring seems to be if that happens to be a trivial tosser for the group, say just the connected component, I must say. So suppose the connected component O, so the connected component, the Picard-Bessel ring becomes a trivial transfer for the connected component over F naught. Then what happens is that the Picard-Bessel extension becomes a purely transcendental extension. So when the Picard-Bessel extension is a purely transcendental extension, splitting the central simple algebra, that actually means there is this Severi-Brouwer variety that that is associated to a central simple algebra, which is a projective variety, and that will have a rational point in the purely transcendental extension. But then if any variety has a point in the purely transcendental extension, then it must be having such a point in the base field. So therefore the Severi-Brouwer variety will have a point in F naught, and for that reason the algebra must split over F naught. So that's in a way is an easy case because we are putting this heavy condition, but otherwise it is not clear whether the Picard-Bessel extension of the differential module, the relative algebraic closure always splits or not. So for example, the result has this consequence. If I have a non-split algebra, then the following groups will not be the differential Galois group of A nabla A. For all those nabla A's that restricts to the base field, when it is restricted to the base field, the constants are algebraically closed. For such derivations, the differential Galois group cannot be any of these groups in the non-split case. So in other words, only matrix algebras will be split by GLN, SLN, and so on. Then I think I will more or less, I think this is my last slide. So what I want to say is there's a recent work on cohomology for Picard-Bessel theory. So where it is shown that projective representations of a differential Galois group of a fixed Picard-Bessel extension. So then the projective representations are in bijective correspondence with those Picard-Bessel extensions that are split by K. So we are looking into this paper, and our guess is that this class of Picard-Bessel extension that is split by K should have some analog in this setup where we are looking at the so you start out with a central simple algebra and differential central simple algebra, and and thinking of it as a module, you split that or you take a Picard-Bessel extension for that module. So you call that this K. Then the Tanakian category will have all these algebras. So the question would be whether all these we also have these projective representations. So whether you can find all these central simple algebras inside this category is something we are looking at, but we don't know anything about it yet. So I guess I finished way too early. So maybe if there are some questions, I will be happy to answer.
Oh, it's actually really good with the time. I think, Alexei, you had a question?
Yes, about this result. So you mean that for each central simple algebra split, etc., you get a representation, or you mean, yeah, what exactly is bijection between?
Yeah, I think the bijection is between, see, you are given a Picard-Bessel extension and therefore a Galois group as well. And then there is a projective representation.
There is one. Okay, so one projective.
There is one, and then corresponding to that, there is a central. See, so basically, projective representations, they classify for central simple algebra. Similarly, there is this differential setup here. So basically, given a projective representation, they would like to know, they have actually associated a central simple algebra that is split by K. From the projective representation, one can construct. So that is the bijection.
Okay. Thank you. I have a quick second question. Have you thought of using any of these for actually solving differential equations?
See, I believe. In fact, I had this talk with Manujit today. So basically, so suppose a differential equation, for example, a differential equation has an algebraic solution. So then what you have is that you do have a Galois extension. Then there is a Galois extension which will contain algebraic solutions of the differential equation. Then one can on top of the Galois extension, you can construct an algebra that contains this, actually as matrix algebra, for example, and you can extend this derivation to a derivation of the matrix algebra. Then the point is that now each of the algebraic solution is actually seen as a matrix with coefficients coming from the base field, and then you have and then it satisfies the differential equation, right? So therefore, maybe perhaps as a test case, say one can work with some things known, and like for example, we know that Airy equation has no algebraic solution. So perhaps one can try to see if this fact can be proved using this. Then there is some, I would say there's some hope, but I haven't tried anything. Maybe there are other angles I haven't thought about it. But this is something that I just today I discussed this. So.
Okay. Thank you.
Okay.
I have a question. Ravi, your slide on the maximal subfields, that seems to suggest that it's very rare to have a maximal subfield which is stabilized by a derivation.
Right. So for example, if I take a matrix, so for example, if I take y prime equals py, where this differential equations Galois group is, for example, unipotent, then first of all if I look at just the matrix ring over the base field, and then I put this derivation, that is, you take the coordinate wise derivation plus this inner derivation by this matrix P, which actually gives you this unipotent group. So then this derivation will not stabilize any maximal subfield, for example. So this is very rare. So most of the derivations will not stabilize any maximal subfield. So when it does, this is the Galois group is going to be quite simple.
So this implies that it's unusual to have a differential cross product structure in some sense.
Differential cross product structure. So by that, so I don't know what you mean by differential.
Well, so start out with a Galois extension and an ordinary Galois extension. And
right. So in the
cycle, and then but of a differential field. Then,
so for example, that construction of Hochschild. First, you
for example,
So that Galois group is a torus that you can easily see, because that derivation is in fact if I let me quickly go back, you can actually see that the derivation is basically given by E sigma is U E sigma. So you can actually see the that. You know, you have this finite Galois extension on top. The
yes, but L itself is not a differential field there, is it?
what happens is the L will, one can think of L is that F naught, you know, that is that, and then the top, which is all gotten by adjoining exponentials, that will appear in the torus part. So I'm only saying the identity component is a torus. So then the relative algebraic closure, so one can think of the relative algebraic closure is this L. And then the top part is basically that this is E sigma. So
oh, and
Okay.
then maybe your last slide explained this, but that is it's nonetheless true that in general that it, given any differential field and a differential Galois group, that you can find a central simple algebra that has that. I'm sorry, given a differential field and a group over the center, that you can find a central simple algebra that has that group as its differential Galois group. In other words, the inverse problem can be, in terms of central simple algebras, is solved by this Wang and Tsai,
right,
theorem.
right. But the question is whether so I know only one way. So for example, if I have a division, if I have a division algebra, then the theorem basically the theorem that I have showed essentially says you know, there are no right ideals. So therefore, the Galois groups. So you can think of you know, the Galois group is reductive in that case. So if I have a division algebra, then the Galois group is always going to be reductive. So, but then given a reductive algebraic group, how do you construct a division algebra, or whether such a thing exists? So that that part is still there. We only know that there are central simple algebras, but which of them? So given a representation for which representation you get division algebra or non-split algebra, cross product. This is so whether there is such a fine classification there or not, that may be worth thinking, but I don't know.
All right. Any other questions or comments?
I had another small question, if we still have time.
Yes.
Sure.
At the beginning of your proof, I think it might have been slide 18.
Okay.
You're setting up this functor S.
Right.
I imagine that is the usual Tanakian fiber functor from the Tanakian
Yes.
category generated by A.
Yes, it is.
So I'm a little bit confused here by so A itself is a ring object in this category of differential modules, but
Right.
not every other object in the Tanakian category generated by A has a ring structure. So what do you mean on the right hand side? So the N here is just an arbitrary object of the category, or just in particular for the image of A itself?
No, so the point is, so what I'm here saying is, I am not claiming anything about other objects. I'm only saying that the differential right ideals of A, they are G-stable right ideals of SA. But this is not true for any thing, any object. It's only for A.
Okay, got it. Thank you.
Yeah. But the hope is, what I was saying towards the end is the recent result by Sui. So he so my hope is all those projective representations you can find something in this category, which is so there will be other objects which are central simple algebras in this category itself. But I don't know whether that's even a reasonable claim or not, because this seems to capture a lot of objects that are split by the Picard-Bessel extension. And since we start with A, you are taking, I mean, there are these obvious tensor products, duals, and all that. So those are all going to be central simple, but there are these other objects when you do subquotients and other linear algebra constructions, but that we don't know what they are. But it appears to me that maybe there is something more to this class of things that are split by K and what they are claiming. But I haven't looked at their proof closely to comment further. So.
All right. So if there's no further questions, let's thank Ravi again for this really nice talk.
Thank you. Thank you.
And so please note that there is no Colkin seminar next week because of Thanksgiving, but I'm looking forward to seeing everyone again in 2 weeks.